All right, in this video, we're going to take a look at a combined kinetics problem where we're using data to determine the rate law and then matching that to a reaction mechanism. So we've got a balanced chemical equation right here, and then we have some experimental data showing the relationship between concentration and reaction rate. And so we're going to use that first to figure out the reaction order for the reactants NO and H2. So if I'm looking, let's look at NO first. So I want to figure out what is the reaction order for NO. I want to pick two experiments where NO changes, but H2 stays the same. So that looks like that is going to be experiment 3 and experiment 4. So notice if I look at these two data sets, it looks as though NO is doubling, H2 stays the same. And if I compare these reaction rates, I will see they get 4 times bigger here. Again, if I want to make this more explicit, what I'm doing here is I'm comparing my concentration, right? So I'm taking the bigger number divided by the smaller number, and I'm saying, hey, look, the concentration of NO is 2 times bigger, and then I'm going to make a comparison of the rates. So again, I'm going to take this, I'm going to do them in the same order. So if I took the bottom number divided by the top number, do the same thing over here. This number divided by this number. When I do that, I end up with 4. And so we know that the, rate is proportional to the concentration to some exponent. So if the concentration is changing by 2 and the rate is changing by 4, the question is, what must that exponent be? And the number that fits there is 2. So it looks like NO is second order, is what we would say. That means it has an exponent of 2 in the rate law. All right, and then I'm going to do the same thing for H2. We want to compare, two reactions where H2 changes, NO stays the same. It looks like that is going to be experiments 1 versus 3. Sorry, 1 versus 2, so the wrong number. So we compare experiments 1 versus 2. Again, we notice that when we, double the, if we compare experiment 2 divided by experiment, 1, we notice that the concentration doubles. And then if we compare the rates in the same order, it looks as though the rate also doubles. So in this case, the rate is changing by 2, the concentration is changing by 2. Those seem to match. So the exponent that fits here is 1. So it looks as though the it is first order with respect to H2. And so the overall rate law is rate equals K NO squared H2. And if you're feeling a little bit lost on the rate law stuff, maybe you can go back and watch earlier videos reviewing how to use data to determine reaction order. All right, so we've got a rate law here. And then if we know a rate law and we have some numbers here, we can actually solve for K. So I'm just going to, do some algebra, rearrange this. K equals rate divided by the concentration of NO squared and the concentration of H2. I can pick any data set. I'm going to use the first one. So my rate from experiment 1 is 1.8 times 10 to the negative 4. I'm getting these numbers just from my data table. And my units I'm also getting from my data table. You'll be given units. They're going to vary based on the problem. So pay attention in particular to what is the time unit. It might be seconds, minutes, hours. In this case, it's minutes. And then NO is 0.0060 molarity squared. H is 0.0010 molarity. So if you plug those in, you get 5 times 10 to the third. And then let's look at the units here. So looking at the units, so this is just the numerical answer, 5 times 10 to the negative third. I want to figure out what the units are. So the units on the top are molarity per minute. And on the bottom, I've got a molarity squared times a molarity. So I'm going to look for any molarities that cancel out. It looks like 1 molarity cancels out. So I'm left with 1 over minutes divided by molarity squared. That's the same as, remember when you divide by something, it's like multiplying by its inverse. So the units here are 1 over minutes molarity squared. You could also write that as, let me just write, or you could write it as inverse. So you either write, let me draw a box around that one. You can either write as 1 over minutes molarity squared, or you can write this as an inverse exponent. So minutes minus 1 and minus 2. That just means that these things would be on the bottom of a fraction. So whatever you prefer in terms of writing the units works out there. But notice how we're just kind of doing some algebra again to try and solve for what our units are. Look for things that cancel or things that kind of, molarity times molarity is molarity squared. We're just looking to simplify things. And then let's see, which of the last step is we've got a mechanism. Notice in this mechanism, we know what the steps are, but we're being asked which is the slow step. So what I tend to like to do in this kind of scenario is I work through the various possibilities. So let's think through the possibilities. So if 1 is the slow step, then the rate is just going to be determined by who's in the slow step. So if step 1 is slow, then that means rate's going to be k no squared. Does that match our rate law? Not quite, because our rate law says no squared times h2. So it doesn't seem like the first step can be slow, because that wouldn't explain why hydrogen's part of our rate law. So let's look at another scenario. How about if what if step 2 is slow? What would the rate law be? Well, if step 2 is slow, then rate would be determined by who's in the slow step, which would be N2O2 and H2. But notice how N2O2 is an intermediate, right? N2O2 is an intermediate. And whenever we see an intermediate, we say, oh, intermediates can't be part of our, rate law. So I'm going to go back and substitute in the things that made N2O2 in that previous step. So looks like N2O2 was made by NO and NO colliding together. So wherever I see N2O2, I'm going to substitute in NO times NO. So that's going to be NO squared, because there's 2 NO molecules. And then there's also that, H2 molecule that's part of the slow step as well. So notice how if step 2 is slow, my rate law is going to be k NO squared times H2. And look at that, that matches my overall rate law. So it looks like the slow step is step number 2. I didn't even work through the possibility of what if step 3 is the slow step, because we already kind of found the right answer. So we're just going to skip analyzing that possibility. And then I want to show that the mechanism is consistent with the observed rate law. I kind of already did this right here. So if step 2 is the slow step, then this is what the rate law would be. So that matches our observed rate law. So check. But the other thing I want to do is show that it matches the overall stoichiometry. So what that means is we want to show that when we add these 3 steps up, does it match the overall reaction? Which, remember, that was given way back up here. Here's the overall reaction. So if we add these all up, we're going to look for things that are intermediate. So like N2O2 is an intermediate, N2O is an intermediate, and then I've got NO plus NO. So that's 2 NOs on the left, and I've got an H2 and an H2. So that's 2 H2s on the left. On the right, I've got 1 N2, and I've got 1, 2, 2 H2Os. So let's double check to see if that matches. If I scroll up here, yep, that matches what we said it should be. So it looks like this reaction mechanism matches what we know about the stoichiometry, and it matches our observed rate law. So this one looks good.